In this video, we're going to talk about a process called Keto-Enol Tautomerism. It's kind of a mouthful to say that. This is basically the interchange of a ketone, or in some cases an aldehyde, to a new sort of functional group called an enol. So let me just draw out the basic type of reaction I'm talking about here. So I'm going to call this the keto form because it has a C double bond O. It turns out that these can undergo a process that converts the keto into what's called an enol. And the reason this is called an enol group is, notice it's got an alkene and an alcohol. So we add those two together, we get an enol. This process of going back and forth between the two is called tautomerism. And it is a reversible process. Now, why does this happen? Might be the next question. Well, it turns out that carbonyls, because they are a fairly polar group and the carbon is partially positive charged, it turns out that if you have hydrogens next door to a carbonyl, and in this case I'm just drawing out the hydrogens, these particular hydrogens are called alpha hydrogens. Okay, so when you're talking about carbonyl nomenclature, if you go one carbon away from the carbonyl, that's called the alpha carbon. And in this case, this alpha carbon has hydrogen, so they're called the alpha hydrogens. These are mildly acidic. So when you dissolve these into water or put them under acid or base conditions, these protons can potentially come off. And if they do so, what they form is something like this. This is called an enolate. So what happens is that in solution, there's proton exchanges that can go on back and forth that allow a ketone to be converted into the enol and vice versa. And again, the reason for that is because of the presence of these acidic alpha hydrogens. Now it turns out, in reality, the keto form in most cases is going to be the favored form of these. So if I were to look at an example of a ketone, let's look at acetone. And let's draw out what its enol would look like if it were to form. Okay, so this is the enol form. I just mentioned that the keto form is typically the more favored form. So if we actually were to measure the relative amounts of these, this one would come out to be about 99.99%, whereas this one would be 0.001%. So it's a very, very minor amount that would ever go to the enol, particularly with ketones. However, when you talk about aldehydes, let's look at the example acetaldehyde. Okay, so this is acetaldehyde. Notice that acetaldehyde does have acidic alpha hydrogens. This is an alpha carbon. It has these methyl hydrogens attached in an alpha position. So if we were to form an enol of this, the enol would look like this. Now, this, even though it's called an aldehyde, in this context of tautomerism, this would be called the keto form, and this would be called the enol form. In the case of aldehydes, the percentage actually is a little bit higher for the enol. So we get about 0.1% of the enol, which is considerably higher than in the case for the ketone. So as we'll see in the next section of the video, it turns out if you have a mixture of aldehydes, they can undergo a very special reaction because of this keto-enol tautomerism. So as I just mentioned, if you have a mixture of aldehydes that have acidic alpha hydrogens on that alpha carbon next to the aldehyde, these can undergo a special reaction called an Aldol reaction. Let me just show you what one of these would look like. And let's again take that simple molecule acetaldehyde and see what it might look like if it underwent one of these reactions. Now to do this, I'm just going to use two different colors. So I've drawn the keto form here, but I'm also going to draw out the enol form. So what can happen is, in solution, there again is an equilibrium of these two that are going on. If the enol is formed, it can now do an interesting coupling reaction. So what can happen is that, let's say this is done in a mixture of water. Water can come over and act as a base to pull off the proton here. And what that's going to do, it's going to allow this carbon right here, I'm going to put a little asterisk next to that, to become now connected to the aldehyde carbon in the keto form. So if we were to draw now the product of this, and this is a fully reversible reaction, we would get the following as our product. Okay, so here's now this carbon, and the carbonyl of the aldehyde has now been converted to an alcohol. I need to show that, actually. I'm going to pick up a proton from solvent. And now we're going to have a new bond formed to what was our enol. Okay, and I'll put a little asterisk next to that carbon. So the new bond that's been formed is this one right here. It's between what was the enol, which is here, and which was the aldehyde here. The resulting product is now called an aldol product, or more specifically, it can be called a beta-hydroxyaldehyde. So recall that in the nomenclature of ketones or aldehydes, the carbon that's just adjacent to this would be called the alpha carbon. The next carbon down would be the beta carbon. This would be called the gamma carbon, and so on. So this is now what's called a beta-hydroxyaldehyde. Now, one of the really neat things about this reaction is that not only can it occur in the forward direction, this is called the Aldol reaction, but notice this is a reversible reaction. If a beta-hydroxyaldehyde were to fragment and go back to these, that's called a retroaldol, or reverse aldol type reaction. Let's just do one more example of an aldol reaction that has a little bit longer carbon chain. These can be sometimes hard to visualize. So let's do a reaction now that uses butanal as our aldehyde. And again, like I did before, I'll draw the keto form in blue, and then I'll also draw the enol form in pink. So in doing this, what's going to end up happening is the enol, oops, let me write that out with pink here. This has water. Say it's going to pull off the proton. We're going to now make a double bond oxygen there, and now it's this enol that's now going to become attached to this position here. And then this will pick up a proton from solvent. So in drawing this out, and this is where things can get a little bit tricky, let's draw out the 4 carbons of butanal. And we need to convert that to an OH here. And now, oops, let me put in the fact that there's a hydrogen right here. So just move that hydrogen right here. Now we're going to make a new bond to this carbon right here. Okay, so if I were to just number these carbons, this is one way to help visualize this. If butanal had the carbon number 1, 2, 3, and 4, this would be carbon 1, 2, 3, and 4. And let's say that I labeled the carbons of the enol with letters, A, B, C, and D. This would be A, this is B, C, and D. So the new bond is actually formed between carbon B of the enol and carbon 1 of the aldehyde here. And so this new bond is the one that's created between B and 1. And notice again that this would be classified then as a beta-hydroxyaldehyde. So this is the aldehyde, this is the alpha carbon, this is the beta, and it has an OH group. So if this were to form in the aldol reaction is the forward reaction. If it were to fragment and go in reverse, that's the so-called retroaldol. The reason we're going over this particular reaction is that it does have a lot of applications when we get into carbohydrates and also metabolism. We're going to run across the aldol and retroaldol quite a bit later on when we discuss metabolism. All right, that's it for the Keto-Enol Tautomerism. And make sure you get a few more practice problems at looking at identifying what the products of these would be. Good luck.